presentation. So Scott Burleigh. Scott Burleigh recently retired from the Jet Propulsion Laboratory, California Institute of Technology, where he was a principal engineer. His career spanned over 48 years of experience in computer software development, including 35 years of software engineering for spaceflight applications. A founding member of the delay-tolerant networking research group in the Internet Research Task Force, Mr. Burleigh co-authored specification
for version 6 of the DTN
protocol, supporting automated data forwarding through a network of intermittently connected nodes, as we know today is very important. And he was the principal author of the specification for BP version 7, Internet RFC 9171. He led development of the interplanetary overlay network ION implementation
of BP and related protocols, which are currently in operation on the International Space Station. He was principal investigator and software lead for the Deep Impact Networking Experiment, which operated an ion-based interplanetary networking router on the Epoxy spacecraft in solar orbit more than 60 light seconds away from Earth for several weeks in 2008. ION was JPL's nominee for NASA's Software of the Year Award in 2010. Mr. Burleigh has been awarded the NASA Exceptional Engineering Achievement Medal, the NASA Exceptional Public Service Medal, and 4 NASA Space Act awards for his work on these communications protocols. So with that as introduction, Scott.
Thank you. This is probably more slides than I ought to be doing, but okay, good. Thank you for that wonderful introduction. It's very, very complimentary and helpful. I'm sure. I will talk briefly about the architecture of interplanetary overlay network. We've got 4 slides here. The first 2 are really sort of motivation. The root principle of the design of ION was to be able to do this, to implement network communications for lengthy, multi-year robotic missions in deep space, conforming to DTN standards. And the idea being that if it'll work there, then it'll work everywhere. Now, that doesn't mean it'll work great everywhere. It's not optimized, for example, for high-speed operations in low Earth orbit, for example. And it may never be. The intent is to enable delay-tolerant networking as broadly as possible as broad as possible, a range of hardware platforms, software environments, operational constraints. So derived from that root principle are these principles underlying the design. It has to be compatible with spacecraft flight software. That is, in a couple of ways. It has to run on real-time operating systems. It was originally designed, this is like going way back, it was really designed to run on VxWorks. It has been exercised on RTEMS, a number of other real-time operating systems, and of course it runs on, it's developed and runs on Linux. It is currently running in operations, I think, on Windows. It has been demonstrated on Android, although nobody's keeping it up. It's designed for very broad portability, including portability to whatever real-time operating system you got, without having to change any significant source code. Maybe even more important than that, it must never ever compromise any other flight software. For that reason, it runs in background. It doesn't get in the way of interrupt-driven flight software operations. And it does no dynamic memory allocation after initialization. Because if it did, it would run the risk of using up all the memory and disabling other flight software that needs to do memory allocation. So this is a JPL constraint on flight software development that we work within from the very beginning. So for that reason, it's got its own memory management system, which I won't go into in any detail, but doesn't use any mallocs, doesn't use new, doesn't use any stuff that does garbage collection, nothing like that. It has its own management of memory. It has to be able to resume operations automatically under those severe conditions, such as a spontaneous, unplanned power on reset of the spacecraft. Like the spacecraft resets, comes back, and it has to at least there will be some data loss, of course. Anything that is in process, it's not there anymore. But there cannot be any corruption of the data structures that comprise the state of the DTN node. It has to be economical because a lot of these platforms are very resource constrained. They have limited bandwidth, they have limited memory, they have limited CPU. And it has to be portable. The real-time operating systems are poorly supported for development, so we do development in Linux and port to everywhere else. So the intent there is you maximize it, maximize the deployment, because the more broadly it's used, the more it gets exercised, the more bugs you find, the more you drive the bugs out, and the more reliable the software becomes. This is a simplified picture. I'm going to put up a more complex picture in a second, but this is the basic picture of the architecture of ION. It is data centric. That is, the basis for the ION design is an object database, the thing inside the dotted line there, and everything operates on stuff that is in the object database. So, for example, there is no bundle processing agent entity. There are daemon processes that perform the various functions of the BPA in succession, and there is a pipeline. There's a queuing mechanism that conducts bundles from start to finish. So in this picture, you see the application says, here's some data I want to send. Here's an application data unit, that issue button, that goes into a queue. The queue is dequeued by a routing capability, which says, oh, it wants to go out. Okay, I will turn it to a bundle, and here's what I will send it. And by sending it, it puts it into a different queue. That is the queue for the convergence layer output adapter. The convergence layer output pulls it out of that queue, transmits it using whatever it's got, TCP, encapsulation packets, to a receiver that then reconstitutes the bundle and dispatches the bundle. And when it dispatches it places that bundle either in the queue of bundles to be forwarded onward, or in the queue of bundles that are to be delivered to the application, and the application invokes a deliver mechanism to acquire that data. So just a little bit more detail. This is the same sort of thing with a little bit of elaboration. These are the pieces of the, in broad strokes, these are the pieces of ION. There is not much more to it than this. I mean, there are more bits. There are libraries that make this stuff up, but this is pretty much how it works. I will desist now. So there's got to be some way to make this stop, but I don't know where it is. There's a button up there that I cannot make go away.
Okay, good. So thank you, Scott. Our next speaker is going to be Felix Flentge, and Felix is working in the Ground Segment Engineering and Innovation Department at the European Space Operations Center, ESOC. He is an expert in space communication protocols and architecture, such as the CCSCS file delivery protocol and disruption-tolerant networking in general, and is advocating the vision of a solar system internet. Felix is actively supporting and promoting these technologies across all space mission families. He's managing a wide range of activities from operational implementation and deployment of communications protocols and systems, interagency DTN demonstrations, up to including academic cooperation. He is actively contributing to standardization and international coordination in these areas at CCSDS, IOAG, IPN, SIG, and various international working groups on lunar and Mars communications, and is here to talk with us next. Felix.
Thank you, Ed. Just make this bigger. So I didn't want to talk too much about our implementation. So I just put a figure on the right. But I think if you think about DTN implementations, what are the drivers? For me, this is basically a software architecture question. So it's not really different from doing architecture as for other software. And for me, there are three elements which drive the architecture of the final DTN implementations. Maybe starting at the bottom, because this is kind of obvious. It's the resources you have, the platforms, if you have these small devices that Felix has shown this morning, or if you have a more powerful computer, it's operating systems, it's the languages you want to use, you may have to use, or you have people who are familiar with the languages. But what's also very important for me is what are the architectural qualities you want to get out of your software. So this is also quite often called non-functional requirements. And I listed a few of them here. And of course, you would like to kind of satisfy all of them, but in the end, there are a lot of trade-offs involved. So if I'm talking to the operational people, so they will certainly say reliability of the software, stability, quality of the software is the most important one. Because if they cannot trust the software, this means they need to have a different operational concept. So for them, it's a very important thing to have something which is bug-free, which is not failing, and if it's failing, that it's at least always failing and not only sporadically failing. Other aspects can be flexibility, reusability, maintainability is also something important for us. We have missions which fly decades, and we have to update software, we have to maintain software, we have to maintain software with different companies over the years. So to have something which is not well maintainable will create a lot of cost for us in the end. Modularity of software is something to consider. So what are actually the functionalities you group together? What are functionalities you develop maybe outside? Do you do a full system? Do you do libraries? Do you do an extendable system? Depends on your organizational structures. It depends on the contracts you have for software development. Usability, of course, is also related to the question, who is actually the user of your software? So is it other developers? If you do a library, do they need to include it in other software? Is it the operator? Is it the one doing the maintenance? So is it somebody you may not even know because you're going to publish it as open source software? Is it experimenters? Is it students? Whatever. So that's also an important question. Of course, always security, performance. And quite often security and performance, they don't go well together. And finally, also things like cost, licensability, which may limit the choices you have in terms of third-party product or frameworks you can choose. So this is something you ideally are aware before starting your implementation. Quite often we don't think enough about it. But if you look into architectures, you certainly see that there are made trade-offs in certain directions. And finally, also the system context, of course, is very important. Could also say what are the interface with the external interface requirements. So of course, the data interfaces, which is obvious for BP. Want to get application data in, should be forwarded, it should arrive at the final user, but also monitoring and control of the implementation itself, configuration, how easy is it to configure, how easy is it to change configuration, and again, user interfaces. I'm not only meaning man-machine interfaces for the operators, but also for the people using the software. Do you want to provide an easy way to, for example, access your library in a scripting language that you can do easy experimentation, things like that. So overall, as I've said, this is a trade-off. You have to be aware what you want to do, what you want to get out of, and you have to be careful to make this trade-off. Just to mention a little bit the trade-off we have done in our current implementation. So it's a Java implementation because we had good Java implementers. It's more difficult to get a C, C++ developers. It's more efficient to develop in Java, because we get results more easily and it's also more maintainable. So this was, for example, one of the choices. And also our current generation of software is all Java-based. We also decided to not have a dedicated routing algorithm. We want to provide an interface to be able to experiment with different routing algorithms. And one specific design choice was also that we wanted to include a full communication protocol stack. So we are not relying on UDP or TCP/CL alone, but we are able to implement convergence layer adapters by basically stacking different, what we call convergence layer elements on top of each other. So for example, we are able to put an SLE layer because this is important for integration with ground station modems. We put a frame layer on top of it. We put an SPP space packet layer on top of it. We might put LTP on top of it. And we are quite able to flexibly configure our convergence layer. We could also put elements in which drop data for testing, or which do some kind of specific adaptations to specific mission implementations. This is, for us, this came out of more historic thing because this is something we found very useful in the CFTP implementation. So we try to replicate this here as well. It turned out it's very, very complex to do it because you can have fragmentation, aggregation on all of each layer. So it turned out to be a choice which is good for flexibility, but maybe less ideal in terms of quality and stability. Yeah.
Great. Thank you, Felix. Slideshow. And please. Okay, our next speaker is Rachel Dudukovich. Dr. Dudukovich is the lead engineer for the high-rate delay-tolerant networking project and networking lead for the Cognitive Communications Project, which features experiments on board the International Space Station and smallsat missions. She has worked at the NASA Glenn Research Center since 2010 in areas focused on space communication and intelligence systems, flight software development, and space simulation. She earned a PhD from Case Western Reserve University, focused on delay-tolerant networking and artificial intelligence machine learning approaches. She is the chair of the IEEE Cleveland Joint Chapter for Antennas and Propagation, Microwave Theory, Electron Devices, Aeronautical Electronics, and Communications. Rachel.
Okay. And put it into slideshow mode. Oh, okay. So I have kind of like a short project overview, but I think a lot of the things discussed kind of play into the overall architecture considerations. So this is the evolution of our project. So originally we were not actually a DTN project. This is a picture of our PI, Daniel Rabel, back in 2009 when he was working on the IROC project, and that was focused on integrated radio and optical communication. And there was a very small portion of the project that was working on DTN. And then around 2015, we started working on enabling optical communications for ISS. And this was called LEO-T, and this eventually evolved into what is called Illuma-T that we just finished testing with. And at that time, we were looking considerably at the avionics as well as the overall software, and DTN was kind of an external module. And this evolved into the high data rate architecture. From there, we talked with our ISS customers, and they kind of said, well, we're probably not going to put this whole high-speed avionics board on ISS, but what we would be interested in would be a high-speed DTN implementation. And that became HDTN. And that we started calling it that around 2019. And at that point, we really started looking at the DTN architecture and seeing what would affect the performance so we could reach gigabit per second rate. And in 2020, we had our first release of a beta version of HDTN to the NASA GitHub. And from there, we worked extensively with Bill, who's here for the Software Development and Integration Lab at JSC, and evolved over time, adding features and robustness into what is now the current version of HDTN, which is 1.3.1. And so this is the HDTN architecture. So we use a message bus, and we have different modules, and the main ones are ingress, egress, storage, and router. We also have separate libraries that are for routing, BPSec, and LTP. And we also have a web interface, API, and CLI, as well as several applications for sending files, generating bundles, ping, and also multimedia streaming. And we support all the major convergence layers such as TCP, version 3 and 4, LTP, UDP, and STCP. And the key kind of things that we were focused on when we were developing it was to have a modular architecture, a message bus architecture. So we tried to avoid locking and the use of semaphores. So everything is kind of message passing in an asynchronous mode. We also are very performance oriented. So things like the storage and LTP were specifically designed to reach gigabit per second rates. And we're C++ based and fully open source. And also the dependencies that we use are platform independent. So we use ZeroMQ, Boost, and CMake. And the benefit of those is that those are all very well maintained and they're also easy for developers to learn and use. We also follow the NASA flight software process. It's called NPR 7150.2b. And so what that does is it ensures requirements traceability, it ensures thorough testing, and just kind of developing a robust and well-documented product. And we've also been very focused on the user friendliness. So we want to have things like graphical interface that people can use to debug and kind of see where are my bundles going, and then putting video tutorials and things like that to have a good user experience. And the use cases that we were using are the ISS high rate gateway. We're also looking into the LunaNet architecture, so lunar surface nodes, but also the relay nodes and gateway. We're also interested in CubeSat architectures, and we recently have launched the CubeSat experiment just earlier this month. So that's, small platforms, but also things like enterprise ground networks like the NSN. And we also have an active component of research and development. So we work with early stage innovations and SBIR programs, and also portions of the advanced communications and navigation technology that's cognitive comm and lunar 3GPP. And so we're working on increasing the technology readiness through standardization, completing on-orbit tests and automated testing and software metrics. So we have, this is an example of the web interface, and we also have a variety of applications. And in future plans, we're working on network management, improved routing, network level visualizations, and then things like subnetting and clustering, and focusing on Moon to Mars applications. And finally, so this is just kind of some of the things we recently completed. We completed a successful demonstration of ISS with Illumity and LCRD. We have a presentation on that on Tuesday. We also have a small set paper on our CubeSat demonstration and another BPSec talk on Tuesday morning. And we will be hosting a workshop on optimizing interplanetary communication at Glenn. So if anyone is interested in that, please contact me. And that was just a shameless plug section, but get it in. So I think that's it for me.
Thank you. And then our fourth. Here. So our fourth speaker is Felix Walter. Felix is the CTO and second managing director of D3TN. He holds a PhD in the area of delay and disruption tolerant networking and has contributed to several publications in the field. At D3TN, he leads the development of the micro D3TN bundle protocol implementation, as well as multiple internal R&D and customer projects. Felix.
Yeah, thanks for the introduction. Just skip to the last slide here, which is the one for the panel. All right, there we go. I think most people in this room have listened to my previous presentation, so I would just like to summarize the main points from it again. Maybe we can get this out of the way a bit. Let's see. Okay, perfect. All right, so talking about the main design principles and the architecture of micro D3TN or micro DTN. Yeah, what are the central design goals behind it? It's supposed to be a very minimal bundle protocol stack. We want to have as few dependencies as possible, but we want to be also very extensible in regard to the code base and in regard to the interfacing with different applications, routing algorithms, and so on, which leads to the second point, which is we want to have a very high flexibility regarding routing, forwarding, and the overall application setup and also the setup in which we can deploy micro DTN. For this, we aim to use well-defined interfaces, specifically for integrating routing and forwarding algorithms and applications, as well as, for example, CLAs, and to be very adaptable in this regard as well. And we also want to be very simple and easy to use. So for example, the system is running in a single process. It's easily invoked using just a single command line command, and it doesn't require any complex configuration files, stuff like that. So it is aimed to be also easy to use in both research and productive use cases. And one of the original goals was developing micro DTN for microcontrollers, and we are still this is still a central design goal to be very portable also to different operating systems, to microcontrollers and so on, which is why we have an integrated platform abstraction layer that we can port the software to different systems. The implementation itself is based on the C programming language. It uses a single process, as I said, which is multi-threaded. There is nothing like a central storage system, something like that, but it rather uses a message passing approach. So we have different tasks, as we call them, which is threads on POSIX systems, and those are connected via queues and pass messages between each other. And those messages, of course, can also contain stuff like pointers to data, so that we don't have to, for example, duplicate payload of bundles. But a central principle we are following here is that there is always only one of those tasks, like owning one of those pointers. So only one task at any given point in time has the responsibility to take care of any given shared object, so that we don't run into issues that like two tasks are taking care of a bundle and acting upon it, and can run into concurrency issues and so on. And we also have this application and routing interface called AAP that I briefly presented in the afternoon, which uses IPC sockets and protobuf for the on-wire representation to attach flexibly applications as well as external forwarding and routing and discovery daemons that can be easily exchanged and easily adapted to the use case that is required for the given network. On the right-hand side, we see a architecture diagram. Basically, those boxes are the tasks that are running inside the micro DTN daemon. So we have different tasks for the CLAs on the reception side and on the transmission side. Those are connected to queues with our BPA core task taking care of the bundle processing, which again has two queues, one in each direction, to interact with our application agent protocol implementation, and this connects to this IPC socket to the external applications and forwarding modules, for example. And then we have queues connecting this bundle protocol agent 4 with the transmission task to send out the bundles again through the CLAs. There can be further tasks that are not depicted here. For example, CLA-specific ones. If we have like a TCP CLA that is listening on a socket, there will be a dedicated task for that. That then spawns reception and transmission tasks for that CLA. But overall, it's still quite simple in this regard. Basically, we can regard this core system, I would say, as a simple bundle multiplexer, which does not hold persistent state in itself. So not inside here, but the persistent state is either in our bundle storage, which is realized as a specific CLA, or it is mostly a static state, I would say, that is, for example, contact plans that are provided to the specific bundle dispatch module that is attached to the application interface that performs, for example, contact-based scheduling. And that's basically a brief overview of the architecture of micro DTN.
Thank you so much. So now, in the second part of the panel, you will watch me fail to close a window. Thank you very much. So in roughly the 50 minutes that we have remaining, we have just spent some time hearing about 4 important bundle protocol stack implementations, 2 in C, 1 in C++, 1 in Java, with different use cases and different deployments. The discussion now is our chance to ask questions of our panel about design decisions, architecture decisions, protocol stack, what worked, what didn't work, how we put things into operation or not. So I'd like to open it up to everyone for questions. Panelists, as you answer questions, we do have microphones here. Please make sure that they're on and that you speak into them so that our friends on Zoom can also hear. And what I would like to do now is turn this over to the audience for questions. And then if we run low on questions, but we will not run low on questions, then we have a few as well. But please, go ahead.
So thanks for the presentation. It's good to see perspective, the different implementations. So if you consider in the context of LunaNet, where there are going to be surface nodes, orbiting nodes, ground nodes, different endpoints and forwarding requirements, using the Lord of the Rings analogy, is there going to be an architecture to rule it all, or do you think that we will never converge to a single architecture with more workforce specific?
I think probably we'll continue to have multiple architectures and implementations. And this was actually a big focus at the agency level for NASA, for DTN. And we went all through, is it possible to just combine into one and things like this? And I think what we resulted in finding was that, really all of these implementations have their own use case and their own purpose. And having more available is great for interoperability. And specifically for like LunaNet, where we're going to have, government nodes, NASA nodes, and commercial nodes. Commercial entities might use anything that they want to. They may have their own architecture. So I think we'll probably still always have a variety, and especially considering the surface nodes and then things like gateway. So those are even different classes of software, where you might have like an experimental rover that's just some kind of little lower level experimental software, and then gateway, which is human rated flight software. That's a significantly different architecture.
Yeah, I also think so that we will have different nodes, and especially in the case of Moonlight or LunaNet, this is completely industry driven, so it's up to them what that's put on it. Also for ground, I think for either, if we deploy DTN nodes, we will try and we will probably succeed to have a single implementation for ground, because we want to use the transmission of, for example, everything we have in ground station, which per se is part of the infrastructure. But what we get in terms of satellite implementation, this is up in the end to the prime build a satellite. So experience from CFDT shows we start with very dedicated mission implementations, but now we see the different clients transitioning to more standard implementations on their own. They don't cooperate on that. There's nothing available in the market. Might be different for DTN, but I would probably expect that there will be specific implementations by different companies.
Yeah, fully agree with Rachel and Philip. I think there is too many different use cases with requirements that tackle all of them with a single unified stack. And yeah, I mean, after all, it's good to have a variety of implementations to choose from so that you can choose the one that fits your use case best. And I think the most important point here is to ensure that all those implementations are interoperable and to ensure that you have standardized, well-defined interfaces that you can make use of and that you can, for example, implement applications against and so on. So we have the first set of standards already defined, like BP and different CLAs, which is very important. And I think maybe in the next step, we need to define more interfaces like the application side interface, or also the CLA, maybe a CLA interface, a unified one, so that we can also maybe exchange modules and bits between different implementations, which could greatly accelerate the development process there.
Just to amplify, I think what everybody else is saying, I think maybe the most important thing is we need to minimize the cost of adopting delay-tolerant networking so that it's as broadly used as possible. And I think a real advantage there is having multiple implementations that suit the perceived use cases of users, and that are all provided, I think, in pretty much all cases, either open source or at no cost anyway. There's no financial friction necessarily involved in adopting DTN. I think that's really key, because that's what we're really all after in the long run is solar system internet where everything works with everything else.
Get the microphone.
Memory management. Memory management? Yeah. Let's make sure it's on, because maybe I don't know if it's watching.
Oh, good.
Memory management. Scott said after initialization, there's no memory or allocation of memory, right?
No more allocation of system memory. That's right.
Then Felix was talking about Java, which in my mind, Java and memory allocation are interesting. So I was wondering, how do you manage memory in your different implementation, especially given that you don't want memory go wild?
Okay, is this working or?
Oh, you know what? I think it probably does. It's lit up.
Careful. Yeah, I mean, with the Java implementation, we are of course targeting ground. Yeah, so requirements in terms of management are not so severe, and basically it's doing it for you. This is one of the advantages. Of course, we do check for memory leaks and things like that, but that's all. Yeah, I think the more interesting question regarding memory is if we are thinking about onboard implementations. So the typical use case now is we're considering a standard spacecraft. Luckily, since a few years, we're able to fly file systems. So data is going into files. Now we want to send the files. Yeah, so we would have to put the files somehow into bundles. Then we would have to get the files or the bundles somehow to a transceiver, which may also include some buffering. which means from what you used to have in packet stores one time, we now, if we are not careful, we have it 3 times. We have it in the file itself, we have it in the bundle, so we have it maybe in the buffer. So there's certainly a requirement to develop clever strategies with pointing to your data somehow, that you can still maintain a file structure, that you have your bundle stored somehow, but that you don't explode in terms of memory requirements. I think that's one of the big challenges we will have for onboard.
And I don't know if this question is coming from, so we were recently looking into this, but there came from headquarters a statement saying, well, now everything should be memory managed, either Java or Rust. And we're saying, okay, well, that's exactly the opposite of what Scott is talking about. And that's in very like MISRA coding standards and the JPL Power of 10 coding standard that says, well, no dynamic allocation. So those are like 2 completely separate paradigms. So for us, we're just kind of going with standard C++ kind of, strings and things like that. So we do have some dynamic allocation. We're looking into what it would take, like if we really wanted to strictly enforce that. So that's kind of a decent level of undertaking. But then at the same time, then there's this mandate of saying, well, C and C++ themselves are dangerous. Don't use them. Use Java and use Rust. So it's open.
Oddly enough, there may not be unanimity within the United States government.
Yeah.
We have to pass this on.
2 points on that from my side. First of all, we are using the standard malloc and free dynamic memory allocation where we need dynamically growing memory. So for things like storing bundles and so on. However, in our microcontroller ports, we also explored custom memory allocators that wrap those functions, and this is very easily possible, so that we reserve like a specific pool of memory just for our DTN protocol implementation, and send all allocation and deallocation calls basically to that reserved part of memory. So we explored this, for example, and this could be used in a use case where we have this requirement to basically have a pre-allocated pool of memory on launch. The other point on that is one I mentioned in the presentation, which is the principle we follow, that only one task at any point in time like owns a given pointer, a given object in memory, so that we don't run into the issue that we have several references to bits in memory scattered around that we have to like garbage collect or so at the end, and this reduces at least the issue that or also reduces maybe the probability of memory related issues in this regard.
Hello, yes. Thank you guys. For me, okay. Just for the sake of looking for interaction between you, let's say I would like to know which is the distinguishing feature of each of the protocol stack that you guys are proposing here. So, for instance, let's say I'm a mission designer, and in which context I would better choose micro DTN or ESA Java implementation or AGTN or ION? In which context are we targeting the difference between you? Just for the sake of discussion of this here.
I mean, for me, this is very easy. If you're an ESA mission, you're going to use our implementation because it's what you get. Yeah, and that's all. Yeah? It's not you to decide. It's
going to be on flight as well as on ground?
On flight, it's different. This is up to the prime. Okay. Yeah, I mean, I'm talking about ground because our deployment is an infrastructure deployment. So basically, all missions using the same. And if they are not following the standard, I have to hit them a little bit. And then I probably have to implement some specific CLE element or something to support them. But in the end, as a mission, you shouldn't have a choice, at least for an ESA mission.
Well, for us, we've been focused on, specifically high rate optical comm. So we have a lot of our design that is focused on the gigabit per second rate. But that being said, we do have other applications and things. But, with C++, some of the things we're looking at is binary size and things like that. So we haven't been focused on doing the super, super small stripped down implementation. We do, I think have the ability to do that. It hasn't been our focus. Certainly if we decided to, say you're going to have a 256 megabyte thing kind of system, it would take time. But I think Brian has worked a little bit on a very small kind of implementation. But our focus has been kind of like the large scale ground networks and then the high rate gateway.
So yeah, I would say use micro DTN if you require very low resource utilization and or high flexibility in regards to the application and routing in space.
I don't know that ION has a particular use case that it's ideally aimed at, other than for a deep space mission. I think for deep space, the constraints on the ION design make it the safest option for missions in deep space now, and it has actually been exercised in like over 15 million miles, that sort of thing. The other thing that I think might be interesting to somebody who was interested in doing ION is that there are a number of features that are sort of experimental within the standards development community that are implemented and fairly mature in ION. And if you're interested in those capabilities, things like reliable multicast and bundle encapsulation with retransmission built into it, and a number of other measures that are not yet standardized, then ION would be the place to look for those kinds of things.
I was kind of asking this from a challenge we faced with HDTN. So I see I was just looking at for instance, the micro DTN architecture where you kind of have the bundles coming in, like inducts or ingress per se, and then you got bundles going out, like egress. But then you have then as you go that design, then a convergence layer like TCP/CL comes along where it's bidirectional, and now your egress can become an ingress, and your ingress can become an egress. I was just curious if you've encountered challenges with that type of stuff.
Let me start on this one. There's an implementation challenge, but it's not a conceptual challenge. You still have ingress mechanisms and egress mechanisms. In ION, the way that's addressed is that there's a TCP convergence layer adapter that is a TCP CLI. It's an input so that anybody can connect to it, and once you've connected to it, it can travel in both directions. So the output is conducted by a thread of the input task, and if you need to make a connection somewhere else, then that also is a natively spawned output thread. So there are and there's actually capabilities for that for UDP-CL as well, because if you receive a bundle over UDP, from a particular socket, you can send back to that socket rather than having a dedicated output to that socket. So those kinds of like nuances in the implementation take some thought, but the concepts are still the same. You still have a mechanism that is going to look at a queue of outbound data and pull things out of it and send it. You have a queue that's going to look at a queue. You have a thing that's looking at a queue of inbound data and processing it. It's just a matter of how you condition that in the code.
Yeah, so if I remember correctly from our implementation, we have basically outgoing and ingoing CLAs. Yeah, and it's not bundles necessarily going in or out. It's quite often frames, or if you, yeah. So that's the difference. What was interesting, so we thought we have this clear separation between receiving data, sending data, but it gets more complex, of course, if you consider something like LTP. Which case something you have outgoing is also, you have somewhere in your protocol stack something which is receiving, which caused some issues initially.
I agree also with Scott. So that's basically an implementation consideration you have to do there. We also have CLAs like TCP/CL supported that are bidirectional. So surely there is some interaction between the receiving end and the sending end at some point where necessary. I cannot remember that it was a huge challenge to implement that.
I have a question. So, you know approximately on how many nodes your implementation is running on an operational basis? Like, say,
Bill, do you know how many nodes are on
I think
ISN?
they're actually running is about 6. I think we have about 50 STCP items, but none of those have all been connected at once.
Oh, so they're nodes, but they're just not running.
Yeah.
Yeah.
That's on the onboard. Yeah, it's
but any other applications, terrestrial or?
Well, and DSN. And also, there's something running on KPLO orbiting the moon right now, and PACE is using ION on the ground. So I don't know. Total, I think on the order of, all right, Delta and so.
Are you talking about the number of nodes in the system?
No, I'm just wondering, you know, how much.
How large the network is.
I mean, as well applied in yours.
Yeah, we don't have a solar system internet yet. Yeah, yet it's not there.
I could speak a little bit. I know that there's KPLO, which is basically a flight demonstration. So this demonstration is really just to show the data. Really none of the hooks around as a routing system that just to show on back and forth. Even on the turnaround for that, research they were unable to implement the retransmission piece for the button protocol. So for full accountability. Right? Okay. So as far as a flight implementation right now, I don't know if there's any flight implementations for full DTN as far as the closest to the button protocol. And well, certainly nothing that's going to grab directional. So we don't have to.
Yeah,
KPLO is LTP on CFTP data down. KPLO did LTP on data packets coming down. The only thing they didn't do LTP on was reliable video. They sent video unidirectional because they only had 600 bit per second of one. So they didn't want to risk having too much acknowledgement traffic. So they just sent the video down as is, and it worked fine.
Sorry, I'll just speak loud with the microphone. One of the things that's difficult about implementing OSR networking in deep space applications is everybody is terrified of having a ground system automatically connect to spacecraft. The people who are best at that are actually the European Space Agency, but theirs is mostly for reliability purpose for retransmission. But everybody leaves with it now, so they're just so afraid of having a system be closed loop and actually do its own retransmission scheduling to get the mission frames done. The mission level. It's a huge hurdle to overcome.
Yeah, I mean, I know this, yes, and we had the same discussion in CFDP, yeah? When we started CFDP, basically the requirement we got from operators, they wanted to be able to acknowledge every single CFDP file directive PDUs going back to the spacecraft. So monitoring file directive PDUs coming in and then clicking send. So this was the initial idea we had, yeah? Luckily, it didn't went like this. Still, today, if you're doing CFDP, every file directive is going through the mission control system and is visible on the command stack. I think this is an important requirement, and this will not go away so quickly. So what we are planning for bundle protocol is also for bundle protocol, for example, for high data rate downlinks. We would assume high data rate downlinks going directly to the ground station, doing the bundle processing in the ground station by doing custody transfer via a node located at the mission control center, which is fine because it doesn't require a lot of data transfer. So I think this principle will, at least for BP, not change so much, but it's maybe not required. The other point is more for LTP or HPRP, where we really want to implement it as part of the ground station. So there I see a big chance doing it for optical communication. Today, optical terminals include retransmission or RQ schemes themselves, so they do retransmissions, and operators do not know about this, yeah, because they basically, vendors just put their proprietary stuff in, and now it's proprietary, which is not good. So we're trying to standardize this with HPRP, and we are trying to work with producers of optical terminals to get it in. And we will have to talk to our operational people that say, look, this is just a protocol implementation. This is part of your optical onboard terminal. It just stays inside there. There's nothing which will ever leave this optical terminal. It will not go to the TC decoder on board, so it's completely safe for you. I mean, this is a strategy. Of course, once we have this capability, we can use the optical uplink. There will be a requirement or request to also use it for command. So then we will to figure out how to get these things together.
We actually have a focus on dynamic routing. So if you're interested in that, that is a big portion of HDTN for the Cognitive Communications Project. And we're actually demonstrating that on the CubeSat that I was mentioning. So we have a piece of software that's called User Initiated Services, and that allows the spacecraft to request a new contact plan. So we look at the data volume on the spacecraft, and then we say, this data needs to be offloaded by this deadline. We issue the request via an API. We receive a new contact plan, and then we use that link. So that's going to be, a portion of that will be demonstrated. Hopefully in a couple of weeks, we're in the CubeSat process kind of checkout, but we've also demonstrated that on a full flat-sat radio test bed. So if you're interested in that, we do have a lot of experience in that, a focus on the routing and contact plan management. For us, we've kind of been, when the first question I think was, what's the number of nodes so that we have deployed? In our ISS experiment, the optical ground station, so there was 3 optical ground stations, and then there was an NSN network, and then that also connected into Mission Cloud platform. So it went through a wide range of nodes, maybe about, I would say 8 nodes, and then on board there was the gateway and then a payload node. So that's about 10 nodes. Kind of, and we've also done a lot of large scale simulations. So not in operational, but in simulations and emulations into the up to 1,000, I think we've done.
And then just one technical problem with closed loop managing, whether it's Q-Service 13 or CFTP or LCP or a bundle protocol, they're uplink greedy, which is a problem for deep space applications. When we have DSN trying to talk to 10 spacecraft simultaneously, we can only talk to 4, you know, and so when we talk to 4, actually we're not talking, we're listening before, and we can only talk to one at a time. So it's very difficult for us to find a way to get that uplink that everybody seems to feel like they want. I mean, even in ESA, the ExoMars Trace Gas Orbiter at Mars right now, almost all of their tracking coverage that they get is bidirectional, uplink and downlink at the same time. And so they come to DSN and ask for DSN coverage, like, well, we can give you downlink coverage, but we can't give you uplink. It's like, this is a pain, because they want that bidirectional tracking coverage. But for deep space applications, there's just not enough antennas out there. So we need to make sure that these protocols are efficient, where they're not asking for a ton of bandwidth to close that loop of data.
Important, quick comment, and then over to Lee. I think Tom will ask you the question, how many in operation? The answer is order 10, but sometimes the spacecraft, because the build time is multiple years, 3, 4, 5 years. Another question is what missions are looking to be deploying bundles and are in construction now. And when we start looking at how the original LunaNet, Moonlight, and other lunar networks are going to go, we start seeing JAXA and ESA and NASA missions that will be exchanging bundles with each other in orders of maybe 10 or so nodes each, which then starts building up a little bit of an operational network where you might have 20 or 30 different nodes in that mix. But more importantly, it allows us to test some of the scheduling and contact graph routing where we can run things in parallel because the moon is close enough so that we can get some level of truth associated with what's happening and build up that confidence in the algorithms. So I think bundle is still locked in with the lunar missions that are being built now.
I just wanted to make a quick comment about the uplink on the Korean Pathfinder lunar orbiter, which I did all the testing. The Korean government decided that, unlike NASA says any data that's uplinked that is command data in it has to be encrypted. The idea that LTP checkpoints and acknowledgements and stuff constitutes command data is very questionable because you don't encrypt the TCP/IP when you do an IP tunnel. So the same thing with LTP. We see no reason for encrypting LTP checkpoint data. That being said, the Korean government, Korean Aerospace Research Institute, said that they wanted all LTP traffic uplink for their spacecraft to be encrypted. So basically, at the Deep Space Network, we had to take LTP apart, take the uplink part of it, and instead of mailing it to the uplink process to go right back up to the spacecraft, it now had to go to a computer through the internet to Korea for them to encrypt with their own encryption because they wouldn't give us the keys naturally. And then they put it into a CLTU and then mailed it back with forward space-link extension. And it worked okay. It's like really cumbersome. And then it was a TCP connection. So we had to have a separate computer with a TCP and keep alive, to keep the connection going all the time. I tell people that our testing with KPLO was 10% language barrier, 10% testing DTN, and 80% trying to get the internet to work between here and Seoul. So keep that in mind. The security folks need to start thinking about whether or not LTP uplinks have to be encrypted because we're insisting no. I'm insisting no.
Well,
it'd be up to you guys.
It depends, maybe. Yeah, for Earth observation missions, we encrypt everything. Yeah, and I mean it's fine to route this kind of traffic via the Mission Control Center.
Any other hints?
Sorry. Felix, you had a requirement about long-term durability. So my question to all of you is how much operational readiness we have in terms of, or the implementation, has in terms of upgrading software components over time, over the DTN.
Sorry, say again. What?
Upgrading software components. So let's say you deploy 96 ION on a deep space. How ready is the implementation right now to be able to upgrade, whether it is the whole thing or specific components, and what approach, if any, has been
Okay. I think this is actually a real, and I think all of the implementations we've been talking about here probably are aligned on this. All the flight implementations is in ION. I'm just speaking just of ION because I know more about it. The intent always was that any portion, any element of the node, all the elements of the node that do things are daemons that run in background, and any of those daemons can be stopped individually, and the daemon task, vanish from the operating system without having to take the whole system down, and then that would enable you to upload a new executable for that function, and then start the same thing with the same characteristics, but it would be different executable, so that you can upgrade in place. You sort of need to be able to do this, certainly for deep space, because you've got you don't want to have to run the risk of shutting everything down just to upgrade part of the system. So upgrading libraries is a different story, but upgrading the daemons that utilize the libraries you should be able to do without interrupting operation of the node. The other aspect of all this is that there's, and I think that, again, all the implementations that support this, there's a fairly high degree of runtime configuration and reconfiguration supported in all of these, in all of the elements of the node, so that things that don't require like major structural changes in the node, like increasing the amount of memory allocated, for example, you can adjust while the node is running and have it just continue. I think that's a really important aspect of the design of anything that's going to be running autonomously on a spacecraft.
And we actually went through this process just recently because HTTN version 1 was what was deployed to ISS. And then during, as they kind of understood the ground architecture and we worked with the team from Goddard, they wanted updates and things like that. And then we also had new features that we wanted to test. So we upgraded to 1.2, and then we upgraded again to a 1.3.1. And I think from the software portion, I don't think it was that bad. The part that was difficult for us is that we had to follow that, like I was talking about the NASA software requirements, which is a big process to do updates and things, as you have to go through for every iteration, it's almost like a complete design and complete set of requirements and documentation. So there was a lot of overhead associated with that to actually dynamically add features while staying compliant with the process. So that was something you kind of don't even think about that part of it, but that was a significant portion. I think also from the ISS side, they have a long lead time for doing that kind of same, paperwork and processing and approvals. So I think it was more on that side and less on the technical side.
Yeah, I mean, as I'm talking about a ground implementation, updating is not so difficult. I mean, the main thing is, we have tightly controlled external interfaces, so we have to make sure that this doesn't change or is backward compatible, of course, but then basically you are able to update anytime we have some downtime in terms of communication.
So yeah, implementational wise, fortunately the C ecosystem is a lot more stable than that of maybe more modern languages like Go or JavaScript or Rust and so on. On the side of our implementation, we are there is one important point we consider in developing our interfaces, which is to be be able to stay backward compatible in the future. This is, for example, why we choose protobuf for our AAP interface now. And yeah, we really plan to be able to support backward compatibility. And this is also operational wise one point we currently discuss with regard to service models we plan to offer for micro DTN in the future, where long-term maintenance and support contracts will definitely be an important element.
Thank you. And just for the record, there are a couple of scenarios that we are analyzing as part of our operational procedures. One of them is security patches. You don't plan for them, you don't know where they come, and you have to deploy it pretty fast. And the other is software updates driven by configuration changes. More often than we would love to, we find situations in which, to change this parameter, you cannot do it in runtime, or this command doesn't work the way it is intended to. So you need to basically update the software, and how you deploy this, the software is already in place. So these are, part of the couple of operational procedures that we are looking at somehow quick deployment without affecting the entire operation.
I think Fred has had his hand up for a while.
This is Scott first, but I want to go to the whole panel on this. I know that ION started life in the source repository, but it seems like now it's been cut over to GitHub.
Yes, that's right.
Is that the long-term plan then?
I believe that's right. I'm actually not that involved in the.
That is the plan. Okay.
Oh, Lee is the authority on this now. Yeah.
And then to the rest of the panel, are you all based on GitHub on your implementations?
Your GitHub.
So we unfortunately don't have a true open source license. We have an either open source license. It's called either community license, so it's licensable in either member states only, and then it's hosted on a public or not so public platform.
So we have a public repository on GitLab, which is very similar. For historical reasons, we were starting the implementation on an internal GitLab repository and then just migrated to the public instance.
Thank you.
I actually have a couple of questions, but let me start with what I think is a long question with probably a very short answer. I wanted to ask about your implementation experience and operational experience with BPv6 versus v7. Did v7 make things better, easier? And operationally, to the extent that you could say publicly, what are the ratio of the two protocols in use in various networks that you deploy? And are there any issues with coexistence or emergency, things like that?
The latter part of that is there is interesting work being done by the guys at Marshall Space Flight Center on using bundle encapsulation to enable backward compatibility between BPv6 and BPv7. And Josh Deaton knows all about that, and he's unfortunately not here today. But that's a thing to be aware of, and is at least a partial answer to that last point. As far as BPv7 and BPv6, as far as I know, I don't know of anything of any BPv7 nodes that are in operation yet. I think everything that's currently flying on ISS is BPv6, except the experimentation you guys were doing. Was that BPv7?
We did both. So we started out with BPv6 because that's what ISS was using. So we kind of built around their requirements. But we also implemented BPv7, and then Goddard was very interested in BPv7. So we tested that. And that's actually the first time that was tested on ISS. And I think between the two, I mean, the things for me with BPv7, I think it is good, but I wish it still had custody transfer, and I wish it still had priority. So those are my little gripes about it.
Yeah.
Working your chair.
So, I mean, we implemented both, and I think in terms of implementation, there's no big difference. If you're starting something today, you clearly should use BPv7. Yeah, so LunaNet is clearly saying it's BPv7, so we're able to get this in. And anything we would do at ESA, we would go directly for BPv7. Yeah, of course, there are some missing features, so we have seen some way to resolve the priorities. So there hopefully will be an Orange Book at least coming out at CCSDS next year. The same thing, we are working heavily on custody transfer, based somehow roughly on the aggregate custody signaling as well. And this is also where we expect to have an Orange Book coming out next year. So there will be something available for the Luna communication constellations. Yeah, unfortunately, we are not able to get to the full standards, but I think there will be something we can refer to in the Luna interoperability specification. So don't use BPv6 because you want to have custody. Talk to us and we have things we can make available already.
Yeah, we also have implemented both and are regularly testing with both. All of our field tests that I mentioned were primarily based on BP version 7. And yeah, in the future, we also want to focus purely on that. Implementational wise, I would agree with Felix. There are no very big differences. The BP version 6 implementation is a bit less complex, I would say. But apart from that, yeah, we should focus on BP version 7 in the future. That's what's standardized.
I think for me, the removal of the dictionary mechanism in BPv6 is just a huge step forward. That almost justifies BPv7 all by itself. That's
a good point.
Yeah.
I can ask my second question as well. Then, operationally, related to the question about the largest number of nodes, what's the largest number of administrative domains that have been networked together, or are primarily all these implementations of single administrative domain?
Sorry, the largest number of administrative.
Largest number of administrative domains that have
domain. Oh, gosh.
Or is it primarily just like within a single operator?
I think we would have to count. So Luna IceCube DTN demonstration involved Morehead State University, JPL, ESA operational networks, ESA relay LAN, and E3TN nodes. So I would say 3 to 4.
Right. There were offstat demonstrations that were 3 or 4 demonstrations as well, 3 or 4 implementations,
but not so many administrative
and
domains. Yeah, I think the offstat typically were maybe 3.
Yeah,
we had for example Experiment Hellenic Aerospace Industries. Actually, was just 2 because of the ESA.
So around about a handful. Yep. Is there another hand? I have one. For the implementation, if we were to look at the specifications that we have today, 9171 and 9172, are all of the implementations fully feature compliant? Because there are many things with all of the extension blocks, all of the behaviors. What is our comfort level with full implementation to the specifications?
We don't have the DTN naming scheme, so we are more focused on what we will get in CCSDS. Apart from this, I think we are compliant.
We have a couple things, so we've gone through this extensively, where we're going through and looking at the CCSDS specs, driving software requirements, and kind of comparing it to our implementation. And a lot of the thing that we don't have so much is some of the reporting features. You know, all of the bundle status reporting, that's probably the one that we're lacking a little bit on.
There's an upcoming RFC that changes the structure of the endpoint IDs in the IPN URI scheme, and that upcoming RFC is not supported yet. I think everything else is supported in ION.
So at the moment, we are fully supporting 9171, so version 7. We are not supporting BPSec yet.
All right, thank you. Any other questions, or are we going to end our contact 5 minutes early?
What's the wasting all that bandwidth?
So, yes, Lee.
I can add 2 minutes. Either schedule. The bundle protocol version 6 plan right now is that version 3.7.2 or whatever the latest version of BPv6 is available. You can compile, you can get the implementation of ION off of GitHub and compile it for either BPv6 or BPv7. In the future, BPv6 version is only going to be maintained for bug fixes. That's it. No more new features. It's just going to be static bug fixes. There's like 30 experiments or something in the ISS that are using BPv6. And if any bugs are found, we'll fix those. All the new stuff is BPv7. So we're telling everybody that BPv7, you got to use that. And you've got to have this wonderful quality of service later. Custody transfer.
The question's a little speculative, but for your implementations, how hard do you feel that they would be in the aspect of if you installed them as a router in one of these kind of experiments to figure out how people can destroy nodes, how hard do you think the implementation would be to access that? In the sense of being able to provide inputs and not have router, as an intermediate router, have terrible.
That's interesting. I think, and we've when you run ION with TCP convergence layer, it's opening a socket, and anything at all can write to that socket, and I think we've had that from time to time, and because the things that come in are not well-formed bundles, they just get thrown away. So at the lowest layer of things that are not well-formed bundles are going to be thrown away. Things that are like a deliberate attack, where it's like a well-formed bundle that is intentionally corrupted. There's error checking for the validity of everything, but the BPv7 itself doesn't provide any protection against being hacked, right? That's what BPSec is for. And I would say that to that extent, the real answer is there integrity checking and authentication provided by BPSec configuration in policy configuration to suppress the attack. And if not, it's kind of wide open, yeah.
Maybe another way of looking at it, if you know the term fuzz testing, where there's potentially things.
Yeah, we have spent quite some effort on making micro DTN fuzz testable. So we have all our parsers and all the deserialization routines are integrated into a library that can be loaded by a specific binary that can then be fast tested easily. And we are regularly performing fast testing on that. And in the beginning we found quite some issues, but that has helped quite a lot now, and we didn't find any issues in the last 1 or 2 years of continuously testing that.
Yes, so we have also an ongoing activity for fast testing of space communication protocols in general, because I think it's also not enough to just do it on the bundle level. You have to start with frames and everything else. So we will see how well we will perform on that. I think the main issue I would also see if you put this router out is denial of service. Yeah, so we currently don't have things in place which would prevent this. So we'll be doing some preliminary work on anomaly detection, security monitoring, but this is all very preliminary. So this will be, I think, one of the main issues.
I think that's what I was about to say. Is I think denial of service is the most likely attack on DTN nodes, and it's unclear exactly what the solution to that is. I think authentication and discarding inauthentic bundles is at the moment is the best we can do, and keep hostile data from getting past the first node in the network. But that node that all that stuff hits is toast.
And for us, we check our config files that they're valid, valid formats, and we're also checking the compliance of our BPSec implementation to the specification. But I think in general, I think that's a whole area of work of checking that, it is actually secure. So, even if we have the authentication and integrity, even the whole architecture, as you were mentioning, is the architecture itself secure. So I think that's the whole project in itself. Yeah.
Great. So we are at time. We're a little bit over. We have used our contact. So I would just like to say thank you again to our panel and for answering all of these questions.